I'm just started to share.
Yeah, sir. Your screen is visible.
Okay. So I need to keep switching. So please give me a couple of minutes.
Yeah, sir.
System is also lagging a little bit.
No problem, sir.
Sorry, I had a disconnection and had to join back. Let me share my screen and keep moving a little. So, okay. So able to see my screen, sir?
Yes, sir. It is visible. Big data and Hadoop slide is visible.
Yeah. Okay. Thank you.
Thank you, sir.
It's going to be a little bit heavy for the system because Hadoop is not small, and so in today's session, what we jump into the looking into a problem statement and see it in action. So let's look into creating an inverted index, inverted search index using Hadoop, Hdfs, Yarn, and MapReduce. And then in tomorrow's session, we will look into HIVE, HiveQL, and Pig, right? So within the ecosystem. So in yesterday's session, we covered the needs of big data, why, what's, where, and how. And today we will try to get as much hands-on as possible. Just a call out and a disclaimer: the kind of content or the breadth and depth of Hadoop is humongous. So I'll try to squeeze in as much as possible in this couple of hours. So please excuse me if I'm missing out something, and then please feel free to have your questions. And we'll start. So so before we jump into the code and in its simplicity is made up of three major layers. One is basically the Hadoop distributed file system. The other one is Yarn. Yarn is basically the resource manager. This is kind of the brains, and on top of which MapReduce jobs are executed, right? So there is Spark and Storm and Hive. These are different other mechanisms similar to MapReduce, which are executed on top of Yarn for processing the data at scale. And there are key distributions in terms of how do I install and run Hadoop clusters in my system, either locally or into my production systems. So the choices we have are around a core Apache binaries, then Cloudera as a company, where duck cutting basically works, and then Horton works, which was also later acquired by Cloudera. So they provide sandboxes, they provide enterprise grade systems as well as open source versions of Hadoop. And MapR is another company which kind of specializes on the distributed file system side of things. And BigTop is another distribution, and BDE is Big Data Europe's distribution, which is basically on Docker. The rest of all the distributions are around VirtualBox and virtual on VM based, while Cloudera has started giving also Docker support. So we will be using Big Data Europe distribution for our demo today. Feel free to stop me with any questions or any expectations as such. Vijay, do we have any specific areas of focus or asks from the audience for today?
1 minute, sir. I'll, one of the participants have requested for things. The participant has asked for yeah, sir. We voted. As for one of the participant request, you want some practical sessions on Hadoop configurations, ETL tools, MapReduce, and other Hadoop ecosystem components like HIVE, Pig, and Spark. So somewhat related to the entire ecosystems.
Okay, so this is where again I'll try to touch upon this as much as possible. But the configurations, I'll touch upon the configuration files as we go by, perhaps like on tomorrow's session in more depth. But when we look at Hive, Pig, and Spark, everything is different in their own and are complex in terms of setting up as well. So I'll try to cover as much as possible, but dominantly I would be appealing for the broader audience as well. So, okay. So, yeah. So we will be using the BD distribution, and the environment which I have set up for myself is based on the Docker part of it. So if I have to switch to my console in a minute. So it comes in a package of Docker Compose, Docker containers for Hadoop, for Yarn, for MapReduce separately, for Hive separately, and Pig separately. So there are links which I can share in terms of like how we will set it up, step by step. For me, just right now, what I will do is to run through this. So I'll keep swapping windows, so please bear with me as I kind of like need to unshare. So I have my Docker setup, which is running, which has the BRE environment with the node manager, the whole Docker setup. So how do I kind of bring it up? Is there are a set of instructions where like we have a GitHub repository which can be used, and can you see my screen? Is my screen visible? Should I kind of zoom it a little bit?
Yes, sir. Your screen is visible.
So now, okay. These are the containers which are running. So currently, now I could stop this. And then restart it. So this is a minimal distribution installation of Hadoop, which you can run on your local system. Yeah. So where do I get this thing from? I get it from sorry. I get it from these URLs, and to start it, all I have to do is to run the compose. It's made up of 5 containers, one for the node manager, one for the data node and name node, and resource manager and history server. So now, what are these containers for? What does this each of these individual elements mean? We will see in a while. Just about just for the curiosity's sake, how how many of the audience are comfortable with this setup? What I'm just showing us, like the data nodes, name nodes, node managers, resource, and basically the cluster itself.
One of the ma'am has raised hands.
Sure. Okay. 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 So for the okay.
Sir, 1 minute, sir. I have participants. I have allowed your mics. Have enabled it. Whenever you want to put a queries or something, you can raise a hands and then you can proceed with your voice. Okay, sir. Okay. So you can continue, sir.
Okay, so for the benefit of everybody, what I would be doing is I'll just do the demonstration and then going into the design aspects. And we will touch upon a little bit of theory as well, where we will cover how the whole ecosystem works. Right. So now the Docker containers are up and running, and my system, my local Hadoop installation is up and running. So I'll log into the Hadoop containers, so into the name nodes. So this is my name node. And so from here, I can start running. I can start run my the Hadoop jobs. So Hadoop comes with a bunch of tools and command lines, and also it comes with user interfaces for monitoring and controlling. So if I have to look at this one, so here's the Hadoop dashboard, which gives me the view of the Hdfs, basically the Hadoop distributed file system, and how what are the components, what are the subsystems which are there, and what are the nodes, and what are the storage types which are there, and it gives me a management console for the health of the distributed file system message, right? So from here I can figure out what are the files. I mean, so HDFS itself is a logical kind of a pseudo file system which sits on top of multiple nodes, and so it kind of gives us the abstraction as if like we are dealing with a single file system in a single machine, but in reality it is doing a lot of things internally. So normal utilities or the normal command line utilities are not going to work. So what are the basic operations that we would be end up doing is, so if we take a use case, we said like we will run through that command. So the creation of the search index, so inverted search. So we would be having data files as input, and these files need to be kind of copied into the Hadoop file system. Then we process it, and then we kind of get to see the output. So if I look at the root files, so I have the inputs which are here. So this is a browser which allows me to kind of take a peek into the HDFS interactively. And if and this is the most easier way of doing this, right? And there is also the command line tools, which I'll jump into in a minute. The other part of the management UI is about the cluster health and the resource manager side of things. So this is more from encompassing everything like yarn and also predominantly I would say like yarn and MapReduce focused. What are the components that make up yarn we will see in a while, but this kind of like is a console which tells about like, hey, if I might have a single node cluster, I might be having a 10 node or 100 node cluster. Now it's going to give me the whole cluster details and the cluster metrics, and this is running with the default configurations, right? And it tells me like how many nodes are running over here. I'm running a default node with um, with with one node. I think I need to enable that port. Once I enable that port, it will be available. But then, there's the concept of racks and nodes, and we'll see what they are in a minute as we go by. and then we get to see how many applications are running or has been run, and this is basically from the you know these are the MapReduce jobs and applications. Again, like there is a construct, there is a structure, there is a a method to the madness over here. So we will see what are the applications and when they've been run and like what has happened over there. So this cluster gives you an interactive view of what has happened. I'm sorry, I need to still open up that 8042 port for a minute. Sorry. It's a 0. Okay, so 8042. So now if I have to bring up that 804 as well, we'll come back to that later. So, and the console also gives us a window into the kind of configurations which have been used to bring up the cluster. And there are tons of configurations. As I said, like I will try to look into some of the key aspects tomorrow as we go deeper. You get to see the logs. You get to look at the server stacks and the processes which are running individually across the nodes across Hdfs, Yarn, and MapReduce. And we have the metrics for each of the key components, including identifying information, data about the data transfers between the systems, queues and processes and time intervals. So these are the metrics again, which can be configured and tweaked through the XMLs, through the configurations we just saw beforehand. And coming back, this is the setup, how it looks like, right? So we have a setup which is running and ready for executing our jobs. Any questions so far? Okay. I see some show of hands. Is there any questions from you, Vijay, right now? Akash and Katyani had raised their hands.
Participants, any queries till the point the sir has explained right now?
Excuse me, sir. So one question is there.
Yeah, please.
Will you please elaborate the Docker download and installation a bit once again?
Yes, I can do that. Okay, let me share my screen then. So there is this repository. Okay, maybe it's easier to share my full screen. Yeah. So, do you see my screen here? Is my screen visible?
Yes, sir, it's visible.
Yeah. So this is an article which kind of explains very clearly on like how to go about configuring, downloading and configuring the BRD stack. I mean, and there is also a brief about the Docker containers. Now we just need to check first, if your system has Docker installed, and do you have Docker Compose support as well? And the minimum required version for Docker Compose and Docker is 20 and above, and while Docker Compose is 1.25 or 1.26 and above. Now, once you have this, we need Git. You could also get a copy of the repository and run it. Otherwise, you can directly use Git clone to get your the BRE setup. So if I have to go to the BRE setup, yeah. So this is the Big Data Europe site. So let me. It'll be easier for me to take it from here. This is the Git repository, and you can just simply follow the you can do a git clone and follow the instructions over here. So what I did was to clone this repository, and I started with Docker Compose. Again, I kept it simple. There are multiple ways to do this particular thing. In this repo, they are doing it in using Docker Swarm and others. But in my case, I'm not using any of those. And I'm creating it, using this simple Docker Compose, what comes along with it. So how does that look like? Is here. Okay, let me exit and then start it back again. So this is the Docker repository which I had cloned, and I've used Docker Compose to start and stop, which I showed again. I'll do it again once more. So I stopped it, and now I will also add a couple of ports. We just saw that a couple of ports were not accessible, so I will add these ports as well and make it useful. Okay. So now I just use nano. So we had exposed port 8080 and the same is as part of the resource manager. Let's look at exposing 8042. What it means is I'm running all the services from inside the Docker containers, and still I would be able to access them through the browser. And since they're running in Docker, and for me to access them, I need to expose that ports and do a port redirection. And that's what I'm doing here. So we have the node manager is 8042. So it's name node, there's a data node, and then yeah, node manager, there is node manager 1, there's a name node, data node, resource manager, and I open up the ports for this one, and We are good to go. Data node is 9864 8188. Data node is that's 64. Resource manager, data node is 8188. So the history server talks about the jobs which have been executed and the information which is related to that. So this is the YAML file, which basically describes the Docker Compose and brings out all the containers which are and the interrelated ones at one shot up. Okay. Any questions? Does it answer the question which you've been asked?
Okay, sir. Thank you.
Yeah. Okay. Now I'll go back and restart the cluster again. So you see all the clusters have started now. Now also the ports should be available. Let's just check that quickly. So we have the local host. Yes, 9870 is available. History server was still not available. 8088. So okay. Check this one. Yeah. So we're good with this 8042. Let's see if 8042 is available for us. Yeah. So this is about the node manager with all the applications and related to the node manager and the internals of that. So this is the resource manager, and we also saw about the history. Resource manager, node manager is 8042, history server is 8188. So let's also look. So we are able to see what is happening inside each of the containers and nodes. Yeah. Okay. So this shows us that like we have a healthy cluster, good cluster up and ready for action, and we can start running it. Okay. Now I showed about this repository, which is from Big Data Hero, right? And I can follow this to set it up. Let me go into continuing with this example of I said like we will look into the example of running that search index, um, building an inverse search index. Before we do that, let us just check if this environment is fully working for us. So I have Hadoop MapReduce standard example, which is available. So give me a minute. Okay. So what I'm going to do is run the standard example before we jump into our detailed use case, just to test if everything is fine. So I'm going to copy the jar file. So when we develop a MapReduce job, for example, what needs to be run. So the code will be something like this, where we have a class which inherits or which extends a standard Hadoop class called configure. And it has certain predefined functions which are overridden. There is a method for executing it from the command line, basically running the job per se. And there is a part for a mapper, right? So the MapReduce part of it. So the map part is about taking the files, processing them like one in parallel, and then converting them into key value pairs, right? And doing the processing and storing it back, while the reduce part of it is about pulling out this information, this key value pairs which has been created, and synthesizing this information around to produce the output. So what it takes in more detail we will see. Now this is the simple Java file, simple program for MapReduce, and I do a build and I create a jar file. And now that's the jar which is here, right? So I'll take this jar and copy that into my name node, and then run it from there. I'll simply follow this instruction so that you can also practice and try it out later and see how easier it is. So I go for this is under Docker Hadoop. Okay. Hadoop. I have this jar file, which is great. So I'll say, sorry. Docker exec basically allows us to get inside
Sir?
the. Hello.
Sorry to interrupt, sir. Sir, can you little zoom your screen so that you can look into the commands, because it's too small.
Yeah, is this better?
Yeah, sir. Yeah, this is better. This is better.
Okay.
Thanks, sir. Thank you, sir.
So so I'm going to copy the jar file into the Docker, into the name nodes. So there's only 3 files over here. So what I do over here is from my local system, I'm going to copy that. Docker CP copies the jar file into the name node instance, into the temp folder. So it is done. I'll switch over here and I will look at this. So now the file has been copied. So now we are ready for the next step. We create a text file with the information or the inputs which are needed. This is a word count demo, so we're just trying to make sure that everything is set up right. So what we do directly, I'll type in some data. It's not there. I'll sample data. Okay. So I've saved it. So we have created a file which is going to be used as the input. I'm going to copy this file back into the same temp folders inside to my Docker container. So in my Docker container, now I have got this file as well. So our input is ready. The application itself is ready. Now it's now time for execution. We are already there inside the bash script. Now we are there. We are having this file in the local file system of the Docker container of the cluster, but it is still not inside Hadoop. So what we try to do is we try to create this folder inside Hadoop for our MapReduce and the jobs to be executed in scale. We need to store this file inside the DFS, the distributed file system. So for which we have a certain bunch of command line tools which are given by Hadoop. Um, and I was talking about the file system right earlier. So we have the user, we have the root, and we have input where I had kept this file. Now I'm going to delete these files. And can take this file inside inside Hadoop's Hdfs distributed file system. So how do I do that? Is I have a command called Hdfs. So there are a bunch of commands for every key subsystems to involve. There is Hadoop. So you can start with Hadoop itself. So Hadoop as a command provides quite a bunch of commands and helper tools which will be used. HDFS is specifically for handling the DFS related activities, reading and writing into files, checking the health of the files, like administering the file system. DFS file system. And looking at and managing the daemon in terms of our the nodes and the clusters, the journal information, everything that is related to the file system management. So what I do now is copy that simple text as the input into sorry so as a HDFS. DFS says use the DFS file system, distributed file system instead of the local file system. If I just use FS with the same command, it will connect me to any of the local file systems which has been configured or a common file system. So Hadoop supports, other than the DFS, it supports AWS S3 and local file systems as well. So I could also use the same command to talk to different file systems. So in our case, I want to put it into the DFS. So DFS put as the command which I have to use, and put sample text DFS put sample. Something. Sorry. Sometimes if okay, what's the problem? Okay. There seems to be a problem. Please give me a moment. So, okay. Um, okay. My bad. Yeah. Okay. Please bear with me. So I had made a very silly mistake. I had put a wrong file. Now the same command, hdfs dfs, put the file, copies it into the dfs. Okay. So I'll delete it again and recreate it. Yeah. So now the file whatever we have created is is copied into the distributed file system. And as it always happens, it's one of those silly mistakes which had kind of it cost us few minutes. So please bear with me. So now we have the text file which has been copied. Now, though the size of the file, for example, if I look at the um, file size, it's hardly around 199 bytes, right? So let me type it out as simple text, txt. So this is the content, which is basically only 199 bytes. But in the Hadoop DFS, it shows as like though the size is here, it is taking a full block with size of like 128 MB because the files are going to be stored in blocks, which we'll see later. Okay, so now we have this. The other way to use the command line to see if into the file system is also the same, HDFS, DFS, and you could use predominantly most of the Linux shell commands can be used here as well. /user /root /input, and it takes a minute, but it gives me the same output, this time from the Hadoop file system instead of the local file system. Okay, so we are good so far. We're ready the output, the input. Now I will run the MapReduce job using Hadoop in the system. To test our cluster. We have both the files here. Now I have run the Hadoop command with the jar subcommand and calling out the jar and the class name of which I want to execute, specifying the input and the output folders. Now it throws me an exception saying the output directory is already there. Okay, so a small glitch. I'll need to kind of clean up the output. I could put it into a different folder as well, but for the sake of our discussion, scroll. The output is there, so clean up the output. Now I'll rerun the command again. So we have a MapReduce application which takes the input from the input folders, processes it, and dumps it out into the output. So is my screen visible? Can you see the job running? Mr. Vijay?
It's visible, sir.
Yeah, so let's wait for a few minutes. So if you look at it though it is very small piece of data, it is taking so long because it's again like by design. So it goes through all the processes. There seems to be some problem. Which service is one of the service seems to be down. Okay. I think I need to stop it and restart it again. can see the job running over here. What is taking time? Okay, there seems to be some issue. I don't think we're able to troubleshoot this right now, but let's go ahead and try with our example which we had started with. Yes. Try one last time. Okay. So Sorry, please bear with me and try to get this thing up and running. Why is this not there? Okay. We did this. Let's see this. Okay, files already existing. Job box. It's not activated. Okay. So let's There seems to be resource constraints and contention. So the job has been scheduled for execution, but it is failing badly. Okay. Okay. Fair. Unfortunately, like then, apologies. So this demo which was working right now had stopped working because of the resource issues. I'll try to get this up and running and fixed for tomorrow. So in the meantime, we can try to continue back with the presentation. That's okay. Mr. Vijay? Hello? Mr.
Yes, sir.
Vijay?
Yes, sir. Yes, sir.
Yeah, there seems to be a glitch with respect to my resources. So I'm not able to run this demo successfully. So there seems to be some contention. So I'll try to do this thing tomorrow. In the meanwhile, would it be okay if I continue with the explanations and the presentation?
No problem, sir. You can continue with the presentation.
Okay. So yeah. So this is like not far from reality, and this is one of the things that like we face day to day in our productions as well. Things which are set up and working. You never know like what changes between your local setup to your production environment. So yeah, uh, this is something like very normal. What we face on ground. Okay, back to the discussion. So we tried to set up the environment using Docker. We did the installations, and we saw the UI and the monitoring tools which help us in trying to troubleshoot. So it was from that monitoring tool I was able to find out that there is resource exhaustion and need to kind of revert back some of the changes, or like I need to try and troubleshoot. So and then no changes to the configurations which have been made, but commands as such. We saw some of the common commands that like what we were using for copying files into Hdfs and reading it and writing it back. You know, we saw that in action. Now there are quite a bunch of commands which are over here across the different categories. We will look into that. But at a glance, uh, what happens within this ecosystem is that like there are three main components: Yarn, MapReduce, and Hdfs. So Yarn has again its own master slave setup. MapReduce has its own master slave setup. At least Hadoop version 1 had that. Hadoop version 2 onwards, Yarn was kind of like revamped totally, and it started extending and supporting more execution engines other than MapReduce itself. And HDFS again, master slave support for ensuring that there is no single point of failures. And if you look at Yarn, Yarn is very much similar and comparable to the Docker plus Kubernetes containerization mechanism, wherein like we have containers, we need orchestration between the containers, and the containers can run processes and applications between themselves. So from where Yarn started as like as a scheduler and as a point of execute as a tool for execution for MapReduce, now it has been extended to be more generic. And yeah, this is the hands-on which I wanted to start with, and then like move on to the discussion part of it. Now we have to do it other way around. So when I take up the single inverted index, the problem statement was around which with I have a document called doc1.txt with multiple words, like cat, sat, mat, and then doc2 again with multiple words around it. Now, if I have to create a search engine and then try to search for cat, and it should give me references to doc1 and doc2. And similarly, if I have to, when I search for dog, it should give me doc2 as the result. So that being the idea. So search engines extensively use this concept called inverted index, and this is also something that Elasticsearch uses as for its preprocessing. Building search engines. So what we do is we try to run through this file, process these files, parse them, convert them each word by word, and try to create a map of saying like, hey, for a keyword-based map, and provide an index to it to say that like in which all documents do we have this keyword occurring, and that being our intent. So from the raw data of you know simple keywords or words in a file, we write a mapper basically to scan through the input data documents and process it line by line, and split the line into separate words, and takes the output of the key and use the file index and create an intermediate output, right? That is something which is done very seamlessly. But then, like, as long as we are giving the output back, we will see in a minute like how this is done in the code as well. So the mapper output keys are added to the output collection, and the reduce function basically does the sorting and you know um, and flattening of you know, against all those lines which have been created. So it kind of like flattens the duplicates and kind of like adds, like, so for example, cat, since it is present in both the documents, and there are two entries which have been created during the intermediate step. The reducer function basically converts that into a keyword which is present against the document references. So you have doc1 and doc2 mapped against the cat as the keyword. So this is our final output, and the reducer does this flattening for it, right? Collates all the file names and then outputs a single record for every keyword. That's the idea. So creation and management of an index of keywords and their occurrences within the documents could have been done differently using normal programs as well. But then, like, when the question comes, like, so say I'm going to crawl an index, let's say 100,000 documents, and it is going to take a day or two to do that. And that's where, like, using this approach helps. And tools like Hadoop help. So it resolves the challenges of overcoming the memory exhaustion issues, and having to deal with a large number of keywords, like trying to split everything at one time and holding them into the memory can be avoided, because so we're kind of like dividing and conquering the processing in small chunks. So, and we could have used intermediate databases, but then the reads and writes to a database would normally lead to performance overheads, and then this is where the erasure coding technique used by Hadoop comes in help, because we take one huge block as a chunk, read it, and then, like, when you write it back again, it is done incrementally, and there are no updates involved over here, right? So if I'll switch back to the code for a minute, and let's see. So So this is the class like for which I had to create the inverted job index. And the main method basically uses a tool runner, so it allows me to run it from my command line as well. Not necessarily needed, but it's good if I have to test it separately. And I feed in the configuration and inverted index job, which is basically my class. I apply the solid principles over here, and you know. Keeping the responsibilities separated and leveraging interfaces. And when I go for the run method, basically like it creates the configuration which is needed and does the execution. And the configuration for the Hadoop job tells pretty clearly. This is how like it's a MapReduce job. Which says that like which uses reflection extensively and says that like, hey, my logic is basically next job class inside the jar, and here's the reference for the mapper and the reducer classes, and and what are the output formats which are going to be used by this MapReduce job, and where this input and output should be kind of like read and stored into, right? So and for the input and the output, I'm taking the arguments from the command line, and that's why you'd have seen the command line parameters which I had given earlier was more with uh, hyphen input and hyphen output. So the CLI library basically passes this. Like I could have given any other folder as well. It takes it, and then like this is the configuration which is needed, and it's like delegating, within a team of people. So if I have to visualize and correlate, we have a small pod of a manager and with two people, and the manager basically like defines what needs to be done and earmarks like who does the reading, who does the writing, and what information where it comes from, and then just gives this particular job um, to the third person who's going to be the executor who would be coordinating it. So that's what happens when you do the run. And if you look at the map or the mapper class, again, this is part of the Hadoop framework itself, where there is a setup involved, and then like there is a map method. Things are trying to be kept pretty simple over here. So in the setup, okay, we have the context which is passed through. The context is kind of the pipe which has access to the Hadoop framework and the dependencies. So I use the context to talk to get the file paths basically from the configurations, and in the mapping, when the files are basically processed line by line, and that information comes as like text and key and value during the map phase. The lines which are read basically like come through the value, and so this piece of code basically splits the words and tokenizing them and writes back to the context into saying that like, hey, here's the keyword and here's the document ID. And when I'm saying context.write, it writes back to the intermediate file which we saw, and that's about it. So this is basically like, one file at a point of time is normally given to the mapper. So we had two files. So when it is getting executed parallelly, so doc1 would be given to one instance and doc2 would be given to another instance. Logically speaking, that's where the document ID comes in. So all the words in the documents are split across using the document ID, and context.write abstracts where it is going to be written out, and the rest all is like the magic from Hadoop and HDFs. Now the reducer, what happens is like again is fed with the key and the values again, um, and this could be one or multiple processes, and we would be getting the word and the document ID as through the values. And then like we kind of like convert them into a hash set, basically, like which is going to ensure that it is going to be unique, and we write it back again. When we do the writing back, again the data goes into Hadoop and HDFS, I mean the MapReduce infrastructure in the framework, and HDFS, I mean sorry, not HDFS, the Hadoop framework does the consolidation. So coming back, um, so what does each of these structures mean? I mean, like, what are the role of each of these are captured over here? I normally would recommend to look at a few books, which is basically Hadoop in Practice and Hadoop in Action. These two books are really great in terms of like giving things more in detail. So um, we created the class for the mapper, so which is basically the MapReduce mapper class, and we use the MapReduce default input formatter, which supplies the keys, through this parameters, right? And the map emits the text in the key value pairs. Um, the rest of the parts we just like walk through and saw. So the mapper is made up of setup, context data, and the key value, which is read and then fed from the file to the mapper. Similarly, for the reducer, it is again the classes are, once the classes are given to the job executioners, the reduce methods are called using reflection and once per unique map output key. So this is the interesting part where that MapReduce framework magic happens. So it is extensively based on that key value hash map kind of a funder. So the problems that like we want to solve, we would want to split it into smaller problems and then like try to get the data and intermediate data in terms of key values. So whatever problem I want to solve, I think it would mandate to take this approach of converting the data into key value pairs and using that. Now, um, okay, both the uh, input and output key value classes are specified for the reducer. Now the reducer like uses the input, the intermediate file, iterates through that, and we are using a hash set to keep the list of all the document IDs, and we try to we concatenate that for every item, and and then we finally write it back using the context.write, which reduces the output, takes the keyword and use the unique doc IDs basically, which has been joined, and we get our output. So we saw the details of like how the configuration itself is defined. So when logically, like if there is a problem which has been given at a scale to be solved, so it has to be split into three parts. One for the execution. It can be well defined, like what kind of data inputs need to be taken, where they are going to reside, and loading that data into the Hadoop file system in the first place. And next is like defining the job, then defining the mapper logic and defining the reducer logic, and then finally, like executing it from the command line. So that's about it. I'll take a minute and and we saw the class monitoring systems in action, and there are relevant commands for Hadoop, Hdfs, Yarn, and MapReduce. We will see some of them. And yeah, before I proceed any forward, I'll take a pause over here and take any questions.
Participants, any queries?
Is it helpful? Is it clear how the MapReduce kind of structure has to be? I mean, is leveraged, and it is fairly different from the fundamental way of writing programs. It's a very opinionated and a very prescriptive way of doing things in a particular way, so that the distributed processing can be achieved.
So you can unmute and speak, participants. Dear participants, your microphone has been enabled. You can unmute from your end and you can ask queries.
Okay.
Yes.
Okay, fair enough.
Sir, no doubts, sir.
Please go ahead.
No queries, it seems, sir. No doubts. As for ma'am.
Okay, fair enough. So let's look into the MapReduce design elements. So the difference between traditional RDBMSs and the MapReduce in terms of like RDBMSs can deal with gigabytes, while MapReduce framework helps us kind of like deal with petabytes, and predominantly for batch processing. But again, like the FFT, Spark, and Flink, and the other new execution mechanisms support real-time processing as well. And while the RDBMS like help in reads and writes, big data is not meant for transaction processing. I mean, OLTP-based systems, what it means is like you can't use it as a data store or a backend updates, or like let's say a microservice for that matter, right? So it's about processing systems, and which doesn't go through changes like fast. So it is write once and read many times is the pattern where it's most useful for. And yeah, scaling is again linear. Integrity is low when we mean that, like it'd be difficult to see if data consistency and relevancy uh, can't be validated on the fly, right? So when there are changes which have been made to different files, you will get it only when you're processing it through, and which could happen, over hours, or like, whenever it is processed. So the fundamental MapReduce design element is around breaking down larger problems into smaller chunks and chain these jobs to kind of process again and again multiple times. So the thought process needs to undergo a lot of change. So from when a client basically triggers a job or submits a MapReduce job, uh, that there is no interactive triggering or like interactive execution of these jobs normally. Once you set it up, then it can be done programmatically to schedule them. Um, the job gets into the Hadoop MapReduce master, right? And from there, it is split into multiple job parts. This could be by the file, by the processes, right? And then basically the input data is fed into the map part of the code mappers, and then the output comes back to the MapReduce framework, which again like does its intermediate storage sorting and sending it back into the reduce, which could happen at a different point of time and in different sequences. So yeah, it splits into multiple internal tasks and schedules them for execution or across multiple nodes, and the output is generated and stored back into the system. So thereby, like the memory usage, even if I'm going to use terabytes of data, the memory usage of these files are of these processes are going to be pretty smaller, more effective. So simplified parallel processing and abstracting the complexities of the distributed processing is one of the key benefits of using MapReduce. So without this MapReduce framework, what it means is like, so if I'm having, let's say, I have to process a CSV feed which is coming from a partner of mine, which is which is having let's say 1,000,000 records, and I need to curate it and then like process, load it into uh, my systems with some analytics. Uh, I will have to invest in writing core Java programs, which are going to use parallel processing using threads and so on. And that alone brings in a lot of challenges to say that, like, hey, can I access this single file from multiple threads? And how do I go about it? So if I can't do it, what do I do? How do I kind of like, then I need to split my file into smaller chunks and then store it and then let these threads basically pick up these chunks and process it. But then when I do that, I also am faced with the problem of like, how am I going to consolidate this? It still doesn't solve my problem. So the focus moves away from building the business need or business solution to building the system components and infrastructure. So that is avoided when we use MapReduce, because the whole distributed ecosystem along with the framework has been provided to us. So we can focus on solving the problems rather than the platform complexities. And it is made possible purely by the functional programming, and it's also inspired by that, but it is possible because of reflection and the functional programming, wherein functional programming paradigm works around the fact that code can be seen as a data and can be moved around, and then instead of like having an application just iterating through the data and applying logic to process, this is more about data being uh, you know what to say the logic being applied over the data, right? So you can have independent chunks of data for which it's the reverse of the traditional ways of processing. The map and the reduce functions, what you say, for example, would be applied on the data files. That's the core of the MapReduce thought process and philosophy. We saw the different parts. We saw the job parts. One scheduled application can be split into multiple job parts. It can have and between the mappers and the reducers, and it goes through the mapping, shuffling, sorting, and the reduce phase, where the data and intermediate data which has been processed and given back to the framework is kind of like flattened. And yes, both the inputs and the outputs go into by default into the DFS, but there are also, but nothing stops the reducers to also, especially the last link of the chain, like to share data into external data sources. So this is like more detailed view of like how we saw what was happening across all the three phases. The map function takes the input as a key value pair, which represent the logical record. Every record from the file which we had is going to be read through, and then like converted into an zero or more output key value pairs. Okay. So if the map function does a filter, it may only produce like applying some condition, and then at the end of the operation it yields a single key value, or like it could also split it into and say that like multiple unique key value pairs, right? So that's about the mapper side of things. Anyway, the input and the output. The reducer function is again based on the final the list which has been created. It basically, though it is capable of doing reducing it to 1 to 0 or to many, normally what we tend to do is to flatten it and then like reduce it to a single unique key value pair, and then write to files. As I said, not necessarily to files alone. The last leg from the reducer part, it can also be written back into any other external sources. So looking at the HDFS side of things from commands which are supported, almost all the Linux commands which we normally run through on a shell are supported in a DFS as well. So starting from cat, more, or changing permissions, copy, disk space related DFDU, disk usage informations. Quite a lot of this, even including find and grep, are available. The syntax of that, what we saw was to invoke these commands through the DFS subcommands of the Hadoop ecosystem, Hadoop subsystems. Yeah. Some more details in terms of let's say change ownership or like copy files, the equivalent of normal copies, dist CP, which is supporting distributed processing, and the variations. I'll not run through them. Security is another aspect. There's a bunch of security related commands and admin commands. But then security is like very limited within HDFS, to the Kerberos protocol, and yeah, so you can authenticate, and then once the authentication is done, the credentials and passwords and secrets can be stored within the credential providers, and you can have Hadoop use the specific credential providers for validating the operations, which let it be reading and writing files, or to the execution of the jobs, right? So that's all controlled from node from a detailed design point of view, how do we kind of go about managing these things? The scale is based upon splitting the data into different nodes and structure. So there is a master node, there is a name node, there is a data node, which are basically key parts of nodes are indexes or topic of content, right? So they tell where this file and the data is residing. And since the systems had any distributed system had to be tolerant, fault tolerant, resilient, and able to recover from failures. Now, what it means is to share or copy the data into multiple nodes and create multiple copies of it. And the moment you create a file and multiple copies of the file, and also split it, so we need to figure out where the chunks or where the copies
Dear participants, if you please reply, can you hear sir voice?
can you hear me now, Mr. Vijay?
I think
Yes.
sir got disconnected.
Yeah, it's audible, sir. Now you are audible.
Yeah, apologies. I think there was some issue.
No issues, sir. Technical glitches will be there. No issues.
Okay. Can you see my screen? Let me go back to my presentation. Yeah. So, we were talking about the nodes, the name node and the data nodes, wherein the actual data is stored in the data nodes, and the name node is acting as the index, which keeps of track of where the data blocks reside, and then when the request is made for getting the data through the Hadoop APIs for reading and writing, it pulls out the right blocks, right files and the right blocks in the sequence and serves them, right? So the name node is a very important node, and when normally it is a single node which is active, and in Hadoop version 2 and later, then they introduced the secondary name nodes and also replication of the metadata, and it's more fault tolerant now. Yeah. So from a storage point of view, so we have the racks. So there is a concept of racks, nodes, files, and blocks. So nodes, we saw the name nodes and the data nodes, and racks are where is a logical, I'll say, a grouping of nodes. So for proximity and for optimized storage and retrieval, where the files are being stored. So whenever a client application basically asks, uses an Hadoop API and for reading and writing, it says that the request goes to the name node. Think about hey, where do I write or where do I read this data from? And the name node tells, sifts through its indexes and then comes back and say you can take this, the blocks from data node 1, 3, and 4, and then gives the data back to the client, and then the client, when it reads the files through the Hadoop APIs, then it takes the data from the actual data nodes, which has been given by the name nodes. Okay, and the blocks are normally in 64 MB or 128 MB or more sizes, because larger, I mean, like for analytics and data processing needs, it's logical to read larger chunks at one go rather than having multiple smaller chunks. And so it is exactly to deal with the volumes, it's better to have multiple blocks, larger blocks. And what specifically happens in further detail, again, what I captured about the communications between the client to the data nodes, and how the data is captured in terms of blocks versus files relationship is visualized over here. So the replication happens. One thing to understand is the replication doesn't happen at a file level, but at a block level. And then like the blocks are replicated across the nodes, and so you're going to have identical copies of each of the block, and by default it is like 3 copies, but it is configurable to either increase or decrease. So if you increase the copies, it leads to more resiliency and failover, but the downside of that is basically the name nodes now need to do more work, and it's not going to be very efficient. Though storage is cheap, it comes at a cost. Similarly, like if you reduce it down to 1 blocks, then you lose out on the resiliency and integrity while you get speed. So there's a conscious trade-off in configuring the replication factors. And the more the nodes, more node information, because like it impacts the name node, because everything of the name node is maintained in the memory, and these has to be super fast. Yeah, and more specific illustrations about like the read and the write operations. So all the reads and writes happen through the memories, and that's why like you're going through the context.read or the context.write, for example, and the job configurations. Everything is via the Hadoop framework. So the stitching of identifying, reading, and stitching of data across different blocks from different. Okay. And scalability and high availability again. So the name nodes keep a copy of their indexes and their metadata into the disk in the similar way as like the other data is stored in HDFS into another node, and they keep each other in kind of like sync over periods. So whenever there is a edit or a change which has happened, which means in the name node, in the files in the blocks level, so that information is synced between these 2 nodes. This is where the journaling comes into the picture as well. So whatever changes which are happening, it is incrementally captured and replayed in terms of like what data has incrementally been added. Since updates are not there into the whole ecosystem, so it becomes much more easier, and journaling is more efficient. And Zookeeper as like another tool is also used to kind of manage the failover between the name nodes. And both it's basically like it's a when we look at the high availability modes, we are looking at active passive failover support. and not necessarily active-active, where all the requests go through multiple name nodes. At any given point of time, there is only one name node which is active, and and when it goes down, there might be a small lag, but the second name node comes up immediately. Okay. So that's about scalability and high availability. So at any point of time, whenever one or more data nodes or name nodes go down, the the name nodes know how to balance it out, and they start routing into like, okay, uh, data active data nodes. We saw again the user interface, the monitoring UI for resource manager. There are also metrics and stuff like which are the configurations are again through the property file. The granular configurations to tweak the performance of the system, and it takes time to master it. Okay, there are a bunch of commands which are again related to the yarn side of things, and that's available through the the MapReduce side of things through the MapReduce commands. And yarn has a similar set of commands to process their node managers, the resource manager, and all this, even the scheduler and all the other components. This we saw. That we can delve more into the scheduler design. What happens once a job has been created and assigned? Since the nature of the whole framework is about distributed processing and stateless processing, not I mean single components cannot be holding in data or processing for a longer time. So you see too many moving parts, starting from a yarn client to a resource manager to an application master to node managers and containers. So this is kind of a logical view, which tells that like hey, I need to create a yarn application which is nothing but a MapReduce job and execute it. So I tell somebody called the resource manager to say that like, hey, here's the job that needs to be done. Go schedule it. And the scheduling, the job might not start immediately. It will start execution based on the resources, the current load, and multiple other factors. Hence, the resource manager's job is very critical over here, and it kind of tend to manage the resources from the containers, and the containers are the actual processes which are executing it, and then you can have granular you know um, configurations for the containers, like some of the payloads, some of the processes might need larger memory and longer CPU times, while the other kind of job example could be having only only a thinner slice of the memory and the CPU, so you can granularly control the configuration. So the application master, is basically created by the resource manager starts, and now and once it hands over to the application master, resource manager becomes free and then starts listening it needs to do. Now, application master is specific for every process or every job which has been given. Like you can think about like one instance of an application master for every job created, and the application master then connects to the node manager and the container to create and instantiate the actual processes. And the node manager is needed because these are the node manager needs to tell, like, out of my cluster, which node is like free for execution, and where it should be executed, right? So to launch and manage the containers, it's kind of like, I have a 64 GB RAM system with 16 cores. So then there is one manager for each of these nodes, and then like that node manager takes the delegated work to create and launch the containers and run it. And once the containers run, the containers, like, keep giving the states back to the application master, and which also bubbles up to the resource manager. So it's a very intricate network of different components coming together, each doing their part in isolation, and so maximizing parallelism. Okay. The node manager's job is basically to create, monitor, and kill containers simply, and it also supports monitoring. So the dashboard which we saw for the monitoring information would ideally be coming from the node manager, and it also runs watchdog processes to kill any rogue containers, like basically where the resources are being exhausted, right? And yeah. So node managers keep reporting their statuses back into the resource managers. Resource managers, like, use that information to schedule other jobs and handle new requests. So yeah, this is how basically the how the yarn subsystem works behind the scenes. A detailed group of components which are performing the activities, and they are overlaid physically onto spare where the actual execution happens. Okay. This part is more about the container and the pool management. Now, we spoke about containers. Containers are the actual processes. So in our MapReduce process, we would have had multiple containers which would have been executing either the map part of it or the reducer part of it. Or you could also run any Linux commands as well. Basically, like, any executable application can be run through yarn, and yarn takes it over, puts it into a particular container, and kind of does the orchestration with through the node manager and the resource manager infrastructure. So the granular configuration of each of the containers help run a container pool, kind of like, in a balanced way, and the node manager takes the ownership of it. So the command snippet, what you see below, is a way to tell that, like, hey, here's an application, just go execute it. It's a shell command. It's like, running a find command, normal find command, using the yarn scheduler. So what it means is you can write your applications, MapReduce, but and you can also create exhaustive workflows with intermediate steps, using existing applications. That's about yarn. I think we are almost at the end of time. I'll stop here, and I'll take any questions before we wind up for the day, and continue with tomorrow.
Dear participants, any queries? We have enabled your microphones. If anybody have queries, you can unmute yourself and interact with sir.
It would be great to get some kind of feedback because I wish normally like we get to
It's not
see.
only about queries, any views, feedbacks, how you felt
Yeah.
about sessions can be shared.
Is this helpful? How is this helpful? Are
Yeah,
you
sir.
getting something new?
Hello, this is Sangeeta, sir. The pace was very good. Okay, we could get it. Thank you.
Thank you, Sangeeta.
Thank you. Thank you, ma'am. Any other participants would like to give a feedback? Okay, so we'll close this today's sessions. Thank you, sir, for the session. We're looking for the next session. Thank you all for joining the sessions.
Yeah. Thank you, everybody. And I'll try to get the demos up and running tomorrow.
Okay, sir.
Thank you.